Hello and welcome. I'm the ghost of chemical engineering yet to come. I know what you might be thinking. Don't judge me on my appearance. This is the future, where people are no longer discriminated against or judged for their looks, their ethnicity, their culture, their orientation, or anything else. They're just simply valued for their skills and valued for their expertise. The future contains many challenges for chemical engineers of your generation. What you will be trying to do a lot of the time is to repair the damage caused by your predecessors, trying to remedy some of the environmental catastrophes that are looming on the horizon. However, when you try and improve a situation, the last thing you want to do is to inadvertently make it worse. So, when I say make it worse, you may not achieve what you set out to do, for example. That's a technical failure. However, you might have a technical success. You may set out and achieve those things that you intended, but for those things to have an unanticipated side effect that makes things worse. So, what we're going to explore in this lecture is a very useful tool for chemical engineers to decide how bad things are currently and whether things are improved or not by a future technology. It's a tool of life cycle analysis. You're going to learn a lot more about life cycle analysis as you progress through your degree course, but it's very important that you're aware of this technique right from the outset. The example I'm going to use is the production of a fizzy drinks bottle. A fizzy drinks bottle made out of polyethylene terephthalate, a man-made polymer. So let's think to start with about polyethylene terephthalate. The graph I'm displaying is a graph of polyethylene terephthalate demand in millions of tonnes per year as a function of time. The time frame I've chosen is your era, your lifetime, between roughly the late 1990s and current time for you, 2020. Aside from the banking crisis of 2008, you can see that demand has risen consistently year on year on year on year. A consequence of this, however, is what I'm displaying now. Catastrophic plastic pollution in the global environment, the marine environment, the land environment, the mountain environment. This is unintended, and it is a massive problem that chemical engineers of the future, you, are going to have to try and remedy. So, in remedying this situation and in remedying other situations, we want to try and genuinely improve a situation. So, I'd like to try and find some good, intelligent questions to ask and then see if we can answer them using this tool of life cycle analysis. So, the first question I would like to try and get answered is, what's the quantitative environmental impact of producing a plastic bottle from PET? The second question I would like to try and answer is that, can we substitute anything in the manufacturing process to try and lessen this environmental impact? The third question I'd like to try and answer is, if we incentivise people to go out into the environment and clean it up and get rid of a lot of the plastic waste that we can find, say by recycling, does recycling cause unintended harm? So those three questions we can answer using the tool of life cycle analysis. What I would like to do now is to describe the 5 steps that you undertake during life cycle analysis. The first is to set out the problem, to define what it is that you're examining and where it's placed. So for our example, we're examining one 500 millilitre polyethylene terephthalate fizzy drinks bottle sitting on a supermarket shelf. Note that I've defined the item, the fizzy drinks bottle, and its location, the supermarket shelf, because both the item and the location will affect its environmental impact. You've got to make the item, then you've got to distribute the item. So, we term the item a functional unit, and in our case our functional unit is that 500 millilitre polyethylene terephthalate drinks bottle, but a functional unit might be, for example, 100 tonnes of sulfuric acid or 100 tonnes of fertiliser, as long as you are clear what that item is. The use might be 100 tonnes of fertiliser used on a farm in Arkansas. So we've now defined where that use is, and therefore as a consequence defined the distribution chain. The second step of life cycle analysis is to say, right, this is what I'm making and this is where it's being delivered. What energy and material do I need to do that? This is where the role of a chemical engineer comes in very, very valuable, because We start off with raw materials. You know, as chemical engineers, stuff about raw materials. We also start off with energy to convert those raw materials into something useful, a functional unit. So what we then have is a defined manufacturing and distribution chain that takes those raw materials and that energy and produces a functional unit in the location that we've specified. Typically, unfortunately, that manufacturing and distribution process will also have unwanted emissions and unwanted wastes, and we need to know what those are. Now, we term that distribution manufacturing process our foreground system. It's the subject of our study. We are interested in the manufacturing and distribution of this fizzy drinks bottle. However, in order to calculate that impact, we need information about other things as well. We need information about the raw materials. We need information about the energy. So we also have a background system. The background system, if you like, supports the foreground system. And we cannot calculate all the impacts of the foreground system if we do not know information about our background system. Now, typically, the background system will be defined as hopefully data that exists rather than data that you have to go out and calculate. Any data that you go out and calculate will be brought into the foreground system. The foreground system, remember, is your subject of study and will be up to you as the chemical engineer to work out in terms of impact. So the third stage is what we term inventory analysis. This is where we do a detailed mass and energy balance over the entire system. Now you can see why chemical engineers are important: mass balances and energy balances. We define and identify the energy inputs from the environment, and we define and identify the outputs to the environment. Very often for chemical engineers, this involves a lot of process flow sheeting, process simulation. Sometimes it involves experimentation as well to try and get data that is simply not known. And so a combination of good experimental skills and good simulation skills run hand in hand for the inventory analysis step of life cycle analysis. The fourth stage is what we term impact assessment. There are 9 recognised environmental themes against which a process is judged. And you gather data that you've accrued and look at your process against these 9 themes. So these 9 themes include global warming potential. It's typically measured in kilos of CO2 equivalent emitted per functional unit. However, it would also include things like the ozone depletion potential, the abiotic depletion potential and the energy depletion potential. So we're looking at depleting our natural environment of resources and energy. It also includes things that pertain to pollution, for example, acidification potential, the propensity to form acid rain. Eutrophication potential is effectively eutrophication of waterways and rivers, for example with unintended nutrients from fertilisers being washed into those river systems, causing algal blooms and killing off river life. There are also environmental themes such as human toxicity and, for example, the ability to create photochemical smogs. And so all these 9 themes form part of the result set for life cycle analysis. The final stage of life cycle analysis is to look at the results and to try and make some judgment and draw some conclusions from them, because all these environmental themes are different. You can't lump them together and say, well, we reduce this set of terms. What you've got to do is to look at them and say, well, if we want to decrease the global warming potential, are we willing to take a small increase in eutrophication potential, as an example? And so there are trade-offs to be made, compromises to be made, and judgments to be made. This is usually a very, very difficult step. So I'd like to highlight a few key points. I've introduced in this part of the lecture a tool called life cycle analysis. It is one of the key enabling tools to evaluate the environmental impact of current and future chemical processes. It gives us a quantitative framework against which to judge improvements and genuinely see whether a planned improvement actually is an improvement. Usually when reviewing the data from life cycle analyses, you have to make a compromise. You have to judge between different environmental categories and maybe be willing to take a slight increase in some environmental categories for a decrease in others. So, in other words, very difficult decisions sometimes have to be made.